Hi everyone. This is a quick explanation about how we go translating some of these projectile motion equations into a model comparing with our observations. So if I talk about the one with no air friction, then the next one will be similar, just different equations. So we have our initial velocity of projection, so the speed v0 and the angle of elevation theta, and after that happens it's really all up to gravity. So those are the two important numbers, and in our spreadsheet I've stored those two numbers here, and these numbers were not measured, these were guessed. I guessed the right numbers a lot of times until I got the best match I could find. And of course gravity, well, we can't change gravity on Earth, that's 9.81. Now remember, these bits here were observations, so time, the x and the y coordinates came from our video analysis. These are all numbers, so just numbers. This is where the formulas start kicking in over here on the model. So let's take a quick look here at our equation number 3. So equation number 3 is really the important equation. I might just cut that out if I can and put that on the other page. So here we go. This is the one I want. Let's just copy that and pop that, say, up here somewhere where we can see it. So the important thing about this equation is that r is our position vector. I've actually transposed in the working on the spreadsheet, I've added the initial position r0 to the other side of the equation, and remembering that the initial position r0 could have an x and a y component. So if you like, the term in the brackets here should be r0x plus what's there, and the term here should be r0y, the y component of the initial location, plus what's in the brackets there. Now let's take a look at this formula. So this formula is d8, and d8 is the initial value of r0x. That's r0 means initial, r means position, and it's the x component, plus d1. So d1 is the speed, so that's the v. Now it's not v0x yet. It will be when I multiply by the cosine of the angle 153. So you see the d1 by cosine of the angle in radians. All of that bit all of that bit there is really v0x multiplied by c8, and c8 is the time value, t is the time value. So that Excel code up there is really just the Excel equivalent of saying r0x plus v0x times t. And because that's the I component, I've done that under the heading of x. Notice the only part of this which is not locked in is C8, it's t, because this is a function of time. Time is going to change, and that means the x coordinate of the particle will change. So I then copied that formula down. Now for the y value, it's a little bit more to it because there's a little bit more to this part of the equation. Again, remembering that we will start with adding r0y. So r0y, the blue cell here, the initial y location, there it is, E8, added to. Now we have v0y. So v0y is the bit that I've just highlighted. So it's the speed by the sine of the angle in radians. So again, 10.9 and 153. So that's the v0y multiplied by time. Again, C8, no dollar signs. Time is variable. We want the time reference to update to the different time values as we copy. Then subtract g over 2. So I put d3 locked in over 2 by time squared, C8 squared. So that Excel code up there is really just the part in the brackets of equation 3 from our notes here about the so then I literally copied those down. That gave me the orange data series, and I put a smooth connecting line between those. Now each of these orange squares is a prediction which we're comparing with the blue measurement. The blue dots were the measurements, the observations, and the orange squares here were the predictions. Now, to start off with, they're pretty close. Can barely tell them apart. Starting to get it noticeable here, and then we're really starting to notice a gap appearing here. Now, of course, this orange line, this prediction, is if there were no air friction, using, just the laws of motion. However, of course, in the real world, air friction exists, as evidenced by the blue dots becoming lower as time advances. So remember, this one, it started from here and shot off towards the left and then came down. Now there's quite a difference. So how do we account for that difference? Well, we can just match it as best we can on the picture, which is more or less what it did, by changing these numbers. So I might have tried 12 and gone, that doesn't look so good. You can see how the dots here at the start, the blue dots and the orange squares are getting much worse, much quicker. So 12 seems a bit much. I think after a lot of playing around, I settled on 10.9 being pretty good. Now, I was not too unhappy with the fact that it diverged here, because I know air friction will have more effect, and the effect of the air friction is more obvious as time goes on. So these few data points to start with, where things were very close, is what made me confident that these numbers were reasonable estimates for my starting speed and my angle of projection. Remember that 153 is measured from the positive x-axis, so I was firing it in the second quadrant. I shot the thing backwards by mistake on the video. Now, these residuals, well, they're just like any residual, but because we have two observation points, an x and a y point, and we have two predictions, then I've just done a residual for the x values, so the difference between the observation and the prediction, and squared. Likewise with the y values, difference between the observed and predicted y value, and squared. And so all those residuals there are positives. Of course, the ones at the bottom get worse. That's these ones over here. And then I just added them all up, the sum of the squared residuals. I added both columns into the one number. Now, of course, the smaller that number, the better my model, because small residuals are what we want. Now, I don't think, I didn't do a residual plot on this one. If I did a residual plot, there would definitely be a pattern. They're not random. They all seem to be, the predictions are all a bit high. So that's where I went into the model with linear drag. Now, of course, the equations for this one are considerably more complex. That's because, and so there's the y value prediction, considerably more complex equations. And what are those equations representing? Well, they are representing the results of our second part of the analysis, where air friction was occurring. Remember, that's our model for air friction there. And where did we end up with? I think we ended up with, this was equation, that's velocity. We're looking for the one for position. Here it is. There's equation 14. That's the prediction for the position of the x component, the Rx, so the x prediction, based on starting speed, angle of projection, mass of the particle, drag coefficient k, and of course E is the constant and T is time. There's the time up there. And then the y value was this formula 15 here. Yep. So once again, more to it this time. That's why these equations, considerably more complicated, which is why these Excel codes more complicated. But really, same process. Follow the way through and that will be okay. Now what did I do for this one? Well, for this one, you'll recognise the starting speed and the angle from my previous worksheet, 10.9, 153 in my case. So just because I'm changing the idea of how I account for air friction doesn't change the fact that I fired the particle at a certain speed at a certain angle. Now remember, gravity is still 9.8, These are the extra parameters that matter now. So these ones, that's the mass which I measured for I think mine was a Nerf ball, and that was, I guessed that number. I literally just changed the number until the picture matched as best as I thought it could. I didn't think I could get much better than that. Is it perfect? Not at all, because my last prediction point is here, but the last observation is way down here. So although the shape of the curve is matching a lot better, there's still work to be done. It's not. It's probably not going to ever get perfect with this model. So this particular model is a model where the drag is modelled as a first power of speed or velocity. Maybe it should be v squared. Maybe it should be v cubed. Maybe it should be v to some power between 1 and 2, like constant times v to the power 1.5. Now, that's beyond us. We're going with this, which is a rather simplistic model for drag, but at least it's better than no drag at all. So can we claim that that model is better than the previous one? Well, probably, because we're doing a better job of matching the shape of the curve. Okay, I hope that's enough to help. Thanks for watching.